Hi students, welcome to the second online video lecture of computer vision. This is on introduction to optical flow. Hope you have gone through the previous lecture on introduction to motion estimation. This is a continuation of that. Okay, let's go ahead. Like the previous video lecture, this has been also an adaptation of the content. Lot of content has been adapted from Professor Aaron Bobbick's lecture on introduction to computer vision on Audacity, and some slides from other sources. Okay, this is a recap slide from the previous lecture. The motion estimation techniques can be divided broadly into two categories. One is the feature-based methods and another is the direct dense-based methods. Feature-based method is in a given image and its subsequent frame, you would be capturing some key features, okay, and then you would be just finding out how those features have moved in the next image, and from that you will be estimating the motion of the object or the scene. As we discussed, this is a sparse, it gives us a sparse motion fields, and this is very suitable when you have the image motion of the order of tens of pixels. The other category is direct dense methods, where at each and every pixel you will be computing the what are the motion vectors there, what are the velocity vectors in the x and y directions, right? And this is what we would be discussing in this lecture and next few lectures. So these and more specifically we will be talking about optical flow methods. Well, to get some intuition about the optical flow methods, this slides helps you. So assume that you have 3 points in 3 different colors as shown on the left hand side of this image, and the subsequent, assume that they are moving, and you have next frame at the next time instance. What you have is, initially let's call it as I of x, y, t. Next time frame you have at t plus 1th time frame you have the second image. The goal is now to understand where the second where these pixels with different colors have moved. So, well, some pixels could have the same color, like for example those on the diagonal pixels, both diagonal element in the diagonal, whichever are there. So what optical flow does is it looks in its surroundings and figures out the one with the same color, and then from that it estimates what's the value of x and y. Okay, this we have seen in terms of colors, but what we in grayscale images would be looking for is pixels with the same brightness value. Assume you have a pixel location at x comma small y in the first frame, has a specific intensity here, and what you assume the constraint, as it says, brightness constancy constraint. So our assumption here is the brightness of the pixels would remain same despite a movement. That's the assumption. So the second frame, which is a slight movement from the first one of the objects within that scene. So what you would look for there is, you will be looking for a pixel that has in its surroundings that has the same brightness constant. Okay, so for example, that's what the last equation has been given there. I of x, y, t is equal to, you assume that it has moved by a small value u in the x direction and a small value of v in the y direction. So you would find out now a pixel which could be at a location x plus u and y plus v, and this u and v being the values to be find out at the end of your process. Okay, and it is in the t plus 1th frame. So that's all you are going to do. Okay, let's now derive the basic equation for this optical flow. So let me move on to a different scene here in my OBS studio. Okay, yeah, this should serve the purpose, right? So let me do the workout here in a notebook here. So what we are going to do is, in the first image, whichever is there, pixel is there at x comma y location at the teeth frame. Now you would like to find out a corresponding pixel which has same intensity. For that you can move a small value of u in the x direction, okay, v in the y direction, and this you are looking at the t plus 1th frame. So in an ideal case, this would mean that what your u and v should be such a way that y plus v comma t plus 1, this minus I of x y t should be 0. Now assume that u and v are small, very small. So again the regular process, you go to your savior is Taylor series expansion. You do a Taylor series expansion for the first term with respect to, for example, being x comma y comma t being your reference, right, plus dou I by dou x. I am dropping writing of x y comma t here for just the briefness, and of course in the x you have u plus dou I by dou y. In there you are assuming it v, and for t what we would do is you consider t plus 1 and t plus t, okay. So then I could write it as dou I by dou t of t plus 1 minus t, so that's 1, okay. This is the first term, minus I of x y t equal to 0. And of course ignoring higher order, you are also ignoring second order terms, okay. Ignore second order, all the second order terms. So then that's what would happen, okay. These two would cancel out. It would give you now dou I by dou x into u plus dou I by dou y into v plus dou I by dou t equals to 0. Let's again use for compactness, let I subscript x would give you dou I by dou x. Same case with the y and t as well. So then I could write this equation as I subscript x into u plus I subscript y into v is equal to minus I t, okay. If you want, this is the equation for optical flow, right. Assuming brightness constancy by imposing a brightness constancy constraint. This is the result of the brightness constancy constraint. You are assuming that brightness is constant, so that's why you are making that equal to 0, okay. You could in fact write it in vector form as well if you want. For example, I could write it as the ix iy multiplied with uv would give me minus it. I could also write it as this as gradient of I and its dot product with u comma v would give me minus it. You would see shortly for a geometrical interpretation of optical flow solution, this second representation would be handy for us. Another point to note here is how many variables are there. What are the variables here? But we need to find out at each pixel the displacement in the x direction and the displacement in the y direction. So u and v are the variables to be computed. And how many equations are there? Both equations are same, except that we have written it in a slightly different form. So you have a single equation here. It means you have multiple possible solutions. If you impose just the brightness constancy constraint at each pixel, if that is the only constraint that you are posing, it has multiple solutions. Okay, yeah, with that again let me come back to the slides mode. Right. Okay, now the same thing has been written here. It is plus gradient of I dot product with u comma v, that's equal to 0, or I subscript x times u plus I subscript y times v plus it equal to 0. This question we answered. It has two unknowns and single equation, so multiple possible solutions are there. Look at here. Let's take a geometric representation of this. In your image, assume that you have this being your there is an edge in your image that you are looking at, and a gradient of it is there. So when you have gradient of I dot product with u comma v, that's what it is giving. Okay, so let me maybe draw this again. Maybe that drawing could help you to understand it easily, much easier. So let me again go back here. Assume that I have a strong edge here. Okay, there is a strong edge here. This is all, fill it with color. So you have this is here the gradient at that point, this being your gradient I. Okay, now the left hand side of the above equation is inner product of u and v. That is what you have there. So that means any it value, you know it, you see here, suppose this is my u and v is giving me this value, for example, that inner product is same as, even if my u and v values are here, or in fact on the other side also. Okay, so all these things would give you the same inner product when you do a inner product with gradient of I. All these values of u and v, this, let's call it u1 v1, okay, call it as u2 v2, and so on. All of them would give you the same inner product, which could be equivalent to, let's say, the it that you are looking at. So this is another way of, see, one way we had looked at is there are two unknowns and one equation resulting in multiple solutions. Another way to look at it geometrically is, you have in the image you have an edge here, gradient perpendicular to it. On the left hand side you have, for example, it is nothing but I x comma y of t plus 1 minus I of x y t. That's a fixed one. For a given image you get it like a fixed. So right hand side you know the value. So suppose that's the value, we are fixing it. So you get that same value for different u, because you are taking only one of the components of it, right? Which is one perpendicular component to the gradient is all that you are taking here, right? So there are multiple solutions here. Okay, let me go back to the mode here. So this is what the component of the flow in the gradient direction is determined. Okay, that's what we are taking. Component of the flow in the gradient direction is what we are taking. And the component of the flow parallel to the edge is unknown. You could have any parallel components, could have any of those things, the way we have plotted. And this is not a new problem, this is an aperture problem. Hope you still remember where we have discussed about this aperture problem. We discussed it in case of corner detection, if you recollect. Harris corner detector we have seen there. For example, in a uniform region you have an aperture problem, you do not really know the corresponding point, identical point exactly, and also while you are moving across an edge to find out even not just detection but finding out the correspondence, there will be multiple correspondences while you are moving across an edge where there is no textural difference or where there is no corner as such, right? The same problem you again face here when it comes to optical flow as well. Again, a quick and a depiction illustration of it. For example, if you have something like this, okay, your object has, the first one is your, assume that your I of xyt and another is xyt plus 1. You could see there is you could see here which point maps to what when you have the big picture. But optical flow you are looking at locally, assume that when you are looking at a very small neighborhood there, you do not know really which point corresponds to what, and you know only in the parallel direction, you have no clue there. Okay, another depiction of this is this. Suppose you only see in a very local region, okay, this appears as if the points have moved, even for us visually looks like the points have moved parallelly. But what could be the case here is, this could be the actual one that getting hindered from you is what has been shown now on the right side. That might be moving in a diagonal, top right diagonal, it might be moving, but that could never be inferred. All you could see is in the perpendicular direction is all, to the edge is all that you could see there. But whatever is there in the parallel direction across the edge, you will not be able to infer. So while it has moved in the perpendicular direction, what you could all say is the movement perpendicular to the edge, but you could never infer to the parallel what is exactly the component. And that same thing we have seen from the inner product as well, right? This is another example of this aperture problem. When you focus yourself in the local regions of those colors, all you would see there while moving, it looks like as if the colors are moving in the apparent motion, looks as if it is moving perpendicularly up. But when you see the bigger picture, what you would see is in fact the true motion is in the parallel direction. So it is rotating in parallel, not in this direction. Okay, this is the very common example here. Okay, again, this kind of illusion is also coming. Notice that the gradient is in a skewed direction. It's not either parallel, either vertical or horizontal. So that gives you this effect as well. This is also in a way can be attributed to the aperture problem. Okay. From the previous illustrations, you could see that optical flow is not exactly motion flow. It's because of the aperture problem. Sometimes it might not give you exact motion of the object. So near an edge, you could only observe the component of flow perpendicular to the edge, and you cannot measure the component which is parallel to it. Okay. Also another thing is, suppose when you would have noticed it, even the die that is there, the checkerboard that is there, which is rotating on a table in the previous class, there also you would see where there is a uniform region. You won't be able to see where it has moved, because that being a uniform region, despite there is a movement at that pixel itself, the constant intensity is there. All you are looking at, the way you are looking at it for its corresponding pixel is that you are looking surrounding it, searching for a pixel that has the same intensity. That being uniform intensity, it could get mapped to any of those pixels. So another case of non-observability. So to repeat again, you could observe components that are only perpendicular to the edge. Parallel to the edge, you won't be able to do that. And also, if the region is uniform, this will not work out. So you cannot observe really any motion flow despite there being a motion flow. Okay, so that's all for this lecture. We just looked at the very basics here in this lecture. So far we posed here only the brightness constancy constraint. in the next lecture we would be imposing few more neighborhood constraints also, assuming for example in a motion all the neighborhood pixels would be moving in the same direction. Such constraints we will be studying. Particularly we will be studying about two specific methods, okay, Lucas and Canade, Horn and Shunk to begin with, and then we go to Lucas and Canade method. Okay, hope this concepts are clear to you, and thanks for watching. See you in the next video lecture. Thanks.